Hello, this is video 32. Yikes, that's not going to work at all. What are you doing over here in the tray even? This is video 32. And this is still the software lifecycle. I'm going to call this software terms, where all the terms have already been introduced, but I just slapped them on the board, labeling a picture, and didn't say what any of them were. Let's be more deliberate, shall we? Box number 1 was the source code. S-O-U-R-C-E, code, if you can't read my handwriting, source, from the source. And just some bullet points about this. Bullet point number 1, this is a human readable printable, P-R-I-N-T-A-B-L-E, printable version of a program. Comma, in a what's called a high level language. Like the Queen's English. Very good. How are you today? No, that's not what a high-level language is in computing. High-level language, comma again, such as, look, Python, Java, bunch of them, JavaScript, C++, Swift, etc. Probably most of the languages, if not all the languages that you've heard of, are high-level languages. Now, this definition itself might be mysterious because you're thinking, well, every program, you can print it out, you can read it. It might not look like English, but it's got English words in it, words like print, and so on, and for, and do, and all that. But no, that's only the very beginning. That's the human readable. It's also another bullet point. This is the version you type in. Comma's all over the place here. Using and you can fill in the blank while I open the green marker to match the previous picture. Using an editor, E-D-I-T-O-R, in a circle like it was in the last picture. The version you type in. So when you are typing in your program, here I am typing in my Python program, you're going to be using an editor. What is an editor? Well, you know what? I think I'll just explain it because I'm going to fill up the board anyway. An editor is kind of like Notepad or Word or whatever. It's a word processor, but in computing, an editor knows a language. In other words, it knows some of the rules of what it takes to construct a valid Python program, and it'll try to help you. It's like spell check on steroids for a computer language. It tries to help you indent properly. It changes words that mean different things to different colors. And if all this sounds ridiculously crazy, you'll see what I mean as soon as we start using one. As soon as the editor knows, well, you know what, they're trying to type in a Python program here, then all of a sudden you're going to see things change colors, change the way it looks, all that kind of stuff that would not happen if you were just typing it in a Notepad or something like that. So you can think of the editor as a smart word processor. Aren't you glad I didn't write all that down? That would have taken up all of the rest of the board. Here's another bullet point. How many bullet points do I have? Maybe this will be enough for this one. As is, can't spell is. As is, this is not runnable by a computer. And that is so surprising. P-U-T-E-R. I'm going to put an exclamation point. The source code itself, it's actually a vulgar concession to us meat-based processors here. It looks kind of like English. It has stuff that we understand, but the computer can't make heads or tails out of it. This is for our benefit. This is so that we can express ourselves in something that sort of makes sense to us. We can express ourselves to the computer. Here, this is what I want you to do, one instruction at a time. But in that form, that's useless to the computer because it doesn't understand English. It doesn't understand any of those words. So what happens next? Well, we cross the line into the next box. Source, what am I going to say? Here, a transition statement. Source code must be, I put the mark back on. Source code must be translated by another green word. I don't know why I'm so terrified of having a marker dry out. I can't just leave the top off of it. I'm going to try to remember to leave the top off. Source code must be translated by a compiler. Had plenty of time to think about that word, didn't you? See, I left it open. Into. I'm not sick, I just got something stuck in my throat. That's the translation line. Source code must be translated by a compiler into drumroll ... to object code. Object code, first bullet point. This is the machine language, M-A-C-H-I-N-E, language. Version of a program. Second bullet point. What does that even mean? The machine language version of a program. It means there are not any English words left around anymore. This is all zeros and ones. Ah, yes, I know what those things are. Those are instructions in zeros and ones, and maybe some data and some numbers mixed in. This is the computer talking there. Yeah, zeros and ones, I can handle that. But this, since it's all zeros and ones now, this is absolutely not human readable. Unless you're Data on Star Trek. He's not technically a human, though. I don't know, maybe Sheldon could read it. They probably write him into the script that way. I doubt that he could really, though. All zeros and ones, not human readable. I mean, it's all we can do to figure out what numbers they are, even if we know in advance its number. But it is computer readable. And I don't know why I have this as a note. I guess I'll make a bullet point that's also a note. Object code is what we in the biz would call machine dependent. This is having so much trouble writing today. I'm sorry. This is machine dependent. What's machine dependent? The machine language is machine dependent. Every different kind of processor, sometimes even different processors within the same brand, several different Intel processor chips, they have their very own machine language that they understand. They don't understand anything else. That's why when you get a compiler that translates Python into machine language, there'll be one compiler for a PC, for example, completely different compiler for a Mac, because the Mac doesn't understand the machine code of a PC, PC doesn't understand the machine code of a Mac, and there are other types of devices that have their very own machine code that nobody understands but them. That's why with the high-level languages, you probably have heard of Python and Java and C++ and all that. The low-level, the machine language sets of languages, the 6502, you know that one? The Intel 86 series, that's a set of machine languages. MIPS, maybe you heard of MIPS? That's what's in PlayStation 3 and just about every cable box that sits on top of a TV. It's in MIPS, MIPS machine language. What language was it written in? Here's a weird thing. We don't know what language it was written in. It could have been written in Python or Java or C++ or whatever. When it's translated by a compiler into machine language, we're no longer able to look at it and reverse engineer which language it started its life in. What that means is you can use different languages to write the same program. Some of these have their own little X-Men superpowers, though, that make them more handy for one type of programming than another. Maybe some of them are really good for writing video game controllers, but they're not so good for writing things that run over the web and vice versa. So these are like little, what are called niche languages. That's actually the term that's used. It's like the little boutiques in the shopping mall. You pick out what kind of application you're going to be writing, and you choose the language to write the program in based on that. What that means is, for people who are programmers, you probably are going to have to know several different languages if you want to be versatile. Wow, that was off on a tangent. This is machine dependent. A different machine has to have a different machine language. That's what that means. Okay. Now then, time for another line. Yes, and I'm going to run out of space. Object code must be combined. I should be underlining these. Source code must be translated by a compiler into, ta-da, object code. Okay, object code must be combined with library code by a linker. Look at this open green marker right here. Linker, L-I-N-K-E-R, to produce, and another drum roll and dot dot dots and another line. But no, I can't leave it like that, can I? Library code, that was the dotted, mysterious, ghostly box in the previous video. What on earth? Well, I don't have room to write it down, so listen carefully. Maybe you want to write this down. The library code are the, it's like little miniature pre-written programs for us to do the hard stuff. Oh no, calculate square root of 2? I don't want to write Python code to do that. I'll use a math library that has built-in square root. You might think, well, you know what? I'm not going to do square root of 2. I'm not going to use library code. I don't need no stinking linker. Stinking linker. I made up a new term. Actually, you do. All the stuff that's too hard for us to write out in Python one line at a time every time we want to do it, all of that stuff, fortunately, is provided as part of a library for us. What complicated stuff might we want to do? Oh, I don't know. How about read from the keyboard? Read a number from the keyboard. What could be simpler? Well, actually, almost everything is simpler. Reading from the keyboard, it's got to look at the cross matrix of which key was touched and what binary code that translates into and where it goes through the bus into your processor. Oh my goodness, it's a ridiculously complicated thing. So if you want to read from the keyboard, you're going to have to link to a library. Another strange, seemingly simple activity, print something to the screen. Again, it has to interact with the hardware in ways that we don't want to get into when we're just doing simple Python programming to write our own little small application to calculate our best score at a video game or whatever it is we're doing our program for. We don't want to get sidetracked by doing all these ridiculously complicated hardware type activities. That's what's in the library. That's why we need a linker. That's why a linker is going to be part of the IDE we're using. Hope I made a case for that. Where are we now? We are up to, oh, well, this was box 3 here, wasn't it? Library code, I was about to do 3 on the board. Put a little 3 box in front of library code. That brings us to box 4. Solomon, please move. Please, please, pretty please. 4, he's not moving. Box 4 is the executable code. My foot's up under him right now. I'm trying to make him uncomfortable enough to get him to move. And all he's doing is coughing, but he won't move. Executable code. Solomon, don't throw up. Good gravy. Executable code. The complete. Finally, we reached the end of the line. The complete, comma, machine runnable. That says runnable. It's not readable, but it's runnable. The complete machine runnable version of a program. Yes, it's still in machine language. Yes, now it has all the stuff. It's a complete package. This, you might have thought, well, why didn't we stop at object code? That's machine language. The computer understands that. The problem is we probably are asking, in our program, we probably are asking the system to do stuff like read from the keyboard and print to the screen and things that should be easy, but they're not. That's why we had to pull in these library routines, and all those get fit together by the linker like a jigsaw puzzle. We got a big ball of wax here that's the executable code, and now that's ready to roll. That's ready to run when you click on the icon and get it loaded into memory. Okay. And I don't know what else to say about that. That actually fits on the board. That's hard to believe. I guess I'll do another quick transition down here, and I hope I can write it clearly enough to read it. Executable code, E-X-E-C-U-T-A-B-L-E, executable code must be, underline executable code, must be copied from long-term storage. You can finish this without me even saying it. Executable code must be copied from long-term storage into memory by a green circle loader, L-O-A-D-E-R. And I'll go ahead and see if I can squeeze this in here. Must be copied from long-term storage into memory by a loader to become a box number 5. I hope it was box number 5. Was box number 5 the core image? I think so. If you saw how ridiculously messed up my notes are that I'm trying to work from here, I would lose all credibility and you wouldn't believe any of this. Executable code must be copied from long-term storage into memory by a loader. The loader is the program you're running even though you didn't know it when you clicked on an icon on your desktop. You're saying, loader, go find the program on disk that's associated with this icon, pull that into memory and run it for me. Well, the loader doesn't run it. It tells the operating system, hello, we're ready over here. When the CPU is available, we would really like to have it, please. That's what the loader does. That was the loader talking, by the way. The loader to become a core image so the program can run. Did I do it? Did I squeeze all that onto one board? Probably at my peril, but I did anyway. I almost feel like this got swept under the rug. Executable code must be copied from long-term storage into memory by a loader to become a core image. The core image is, the reason it's called an image is almost like a picture of your program. A digital picture, zeros and ones, a digital image of your program as it exists out on the long-term storage. It has to be copied into memory, and then it's called a core image. Why do we need all these pieces? Well, you can actually go back and reverse engineer. You got to have this because you got to be able to type in something. Imagine if you had to type in your program using 2 fingers and nothing but zeros and ones. I doubt very seriously very many people would become programmers. So we need that. We need the editor so that we can do that. Then we got to translate that into machine language, or the computer is not going to be able to make any sense out of it. Now that it's all zeros and ones, it's still not complete. That's the weirdest step, perhaps. Our object code is really just one piece of a jigsaw puzzle. The other pieces are the library routines that we are invoking. That's the word to choose. We've got to invoke the library code to read from the keyboard and print to the screen and calculate square root of 2 and all that other weird stuff. But the linker puts all those together. The executable code is the picture, the puzzle all put together. But the executable code is sitting out on long-term storage waiting for you to run it. It's not going to run until you say, let's go. You say, let's go by clicking on the icon or whatever it is that you're doing to start running a program. And the loader copies it into memory. It becomes a core image. And voila. The loader does tell the operating system, please run this program now. And the operating system will put it in line. And as soon as it's its turn to run, it will run. There. Is that everything? On a core image. Oh, yeah. Here's the parting thought. You can write this down there if you want. The core image disappears when the computer power is turned off. Of course it does. It's in memory. Memory's volatile, meaning when the power goes, so goes the contents. See how much of this stuff you already know? Now you've got words to map onto it. All these are words that have to do with the software that we'll be running so that we can write Python programs in our IDE and do all this stuff. The IDE is going to cover all this for us. It's just amazing. It's a miracle. I can't wait. I'll see you online.